Okay, I had paused recording as I was waiting to admit you guys into the session. So we've seen that if we have a population P that has a size of capital N, then we can calculate the population mean, in that the population mean will be considered, the population mean mu will be considered to be the average of all units in the population. That is how we calculate the population mean. However, from this population, you draw a sample S that has small n units. And with these small n units, you can calculate the sample mean X bar. So the sample mean X bar is calculated based on the sampling units. So you have the sampling observations. So we are going to have X bar as the average of all sample observations. Now, this X bar is considered to be an estimator of the population mean mu. It is considered to be an estimator for the population mean mu. So it means that we can confidently use the sample mean to estimate the population, the corresponding population parameter, which is the population mean. Now, because we have used a sample to estimate this particular quantity of the population mean, what happens is that in most cases, in any other case where you are using samples to estimate population parameters, we'll find that population estimates, or rather, we'll find that these estimates sometimes they may not, most of the times they may not be equal to the population parameters, in that, remember this X bar is the estimator of the population mean. And when you have actual values of the sample, for example, let's suppose that our sample S consists of units 1, 2, 4, 5. Let's consider our sample to have these units. Then from this sample, you can calculate an estimator X bar to be equal to 1 plus 2 plus 4 plus 5 divided by 4, because that is the size of the sample. So if we do so, whatever we get will be, we are going to get a value of X bar, which in this particular case is going to be 3. Because this is 7 plus 5, 12 divided by 4 is 3. Now, for this particular sample, X bar is equal to 3. Now, this value of X bar that has been calculated using the sample units, we call it a point estimate. When you use actual observations from the sample to calculate X bar or any other estimator, what you get, we call it a point estimate. What you get, we call it a point estimate. So in that particular case, you find that this is no longer an estimator, but an estimate. Now, that brings us to the point where we need to clearly distinguish. An estimator is a function. An estimator is a function of your characteristic. An estimator is a function of your characteristic. So for instance, in this particular case, you can see that we are having a population from which we are drawing a sample, and you can see that our estimator X bar is is defined as a function of the observations that you got from your population. So an estimator is a function. An estimator is a function, but a point estimate is not. Once you have actual data and you calculate a value for that estimator, what you get is a point estimate. And what we are saying is that these point estimates, rarely will they be equal to the population parameter. Rarely will they be equal to the population parameter, meaning that there is a sampling error. There's always a sampling error. So a sampling error is the difference between the point estimates and the population quantity. Now, once you have that sampling error, it is ideal that ideally we are supposed to ensure that the sampling error is as minimum as possible. But that cannot be the case because we have used a sample to estimate this particular quantity. So it means that we now need to find a way in which we can calculate our we can calculate our, or rather we can estimate our population parameters without restricting ourselves to a particular quantity. And that is where interval estimation come in. Now, in interval estimation, what happens is that we are trying to find a general approach of estimating your population quantity such that it lies within a particular interval. So that means that we are now going to consider a scenario where our estimator, for instance, in this particular case, we are going to consider a scenario where our estimator lies within a particular interval I. And once we are able to identify this interval I, then we say we have an interval estimate. We have an interval estimator for our population parameter. Now, for us to be able to calculate this interval estimator, it is important that, first of all, we define our significance level. Our level of significance is very important when we are trying to identify this interval of estimates of our parameter. Now, if alpha is our level of significance, if alpha is the level of significance, then it means that the probability that our estimator X bar lies in the interval I is equal to 1 minus alpha. If alpha is the level of significance, then it means that the probability that our estimator X bar lies in a given interval is equal to 1 minus alpha. So we need to find this interval I. We need to find this interval I so that we can now be sure the range within which we expect our values to lie. Please just give me a moment. Okay, so we want to identify the interval within which our estimator is going to lie. Now, once we are able to identify this particular interval, then we can say that we are 1 minus alpha% sure that our estimator lies within that particular interval I. Now, the interval I is a real interval, which means that it's an interval that lies within the real number line. And therefore, we should be confident that at a particular level of significance that is expected. Remember, like we said, this level of significance is very important. The level of significance is very important, and therefore it allows us to know with some degree of precision that our estimator will be in that particular set of values. So now, just now in estimating these intervals, we can use a two-tail approach, or we can use a one-tail approach. Now, if we use a two-tail approach, what that will imply is that we are considering the curve of this form. Our curve is going to be considered of this form, and we have these two tails being the rejection regions. So if alpha is the level of significance, then it means the lower tail takes whatever is in here is 1 minus alpha, and then the tails share the spoils. So this is alpha over 2, and this is also alpha over 2. So that's the probabilities, the area under that curve is always equal to 1 or 100%. Now, that is if we are considering these two-tail tests, and mostly it is the two tails that we use to derive these confidence intervals. It is the two tails that we have to define. So in this particular case, we are going to suppose that the probability that our estimator for the sample mean, lies between some quantities Q1 and Q2 is equal to 1 minus alpha. The probability that X bar lies between two quantities Q1 and Q2 is equal to 1 minus alpha. That is what that expression means. So the task is to find the exact value of Q1 and also find the exact value of Q2. Now, to be able to find these exact values of Q1 and Q2, what we do is we perform a procedure that we saw last week. We standardize X bar, or we standardize this quantity. Remember, last week we saw that the test statistic, we have two test statistics. We have a test statistic that was Z. We had a test statistic, one was Z equal to X bar minus mu all over sigma over root n. That was one test statistic, and this had a standard normal distribution. That is, when you perform this operation, this random variable now has a normal distribution with mean 0 and variance 1. We also saw another test statistic T, which was equal to X bar minus mu all over S divided by root n. And we said this one has a student T distribution with n minus 1 degrees of freedom. So these two test statistics, depending on your sample size, these two test statistics is what you are going to use in trying to derive this interval or derive the exact values of Q1 and Q2. So what we are going to do to this particular expression here, is that we are going to standardize it, in that we are going to write it in this form. We are going to write it in this form of Z. So in standardization, ideally what we do is that for each quantity involved, you must subtract the population mean. You must subtract the population mean and divide by, or rather, this mu is the population mean, but we saw that the expectation of X bar is what was equal to mu. So if you have this we have that, and then we also saw that the variance of X bar was equal to sigma squared over n. That was the variance of X bar. So in standardizing, every quantity you must, depending on the statistic, on the estimates, or rather the statistic you are talking about, depending on the statistic you're talking about, for each quantity, you must subtract its corresponding mean and divide by the corresponding standard deviation. That is how we perform a standardization approach. And once you are able to do that, whatever you end up having is a standard normal random variable. So we are going to do that for this particular expression so that we come up with the values of, we come up with ways in which we can calculate the values of x1 and x2. So we are looking to find these quantities. We are looking to find these quantities. So we are going to perform the operation. So we are going to perform the operation of standardization. So for each, because X bar has a normal distribution, X bar has a normal distribution with mean mu and variance sigma squared over root n, then it means that these quantities Q1 and Q2 within which X bar lies are also normal. They are also normally distributed with they come from the same distribution and they have the same, they are independent with the same distribution. That means that if X bar has this distribution, then it also implies that Q1 and Q2 also have the same distribution with the same parameters. That is what we mean by identically distributed. They are independent, yes, and identically distributed. So to standardize that, it means that we are going to have Q2 minus mu over sigma over root n less than or equal to X bar minus mu over sigma divided by root n less than or equal to Q2 minus mu all over sigma over root n. Now, this is what we do to have a standardized quantity. Now, in this particular case, the next thing we'll do in this case is that we are going to have, we are interested in the interval. We are interested in the interval Q1 and Q2. Apologies, this is supposed to be Q1. That is supposed to be Q1. So we are interested in that interval. So we are going to use the sample quantities to estimate the interval within which we expect the population mean will lie. So that means that we have to do all mathematical operations to have an interval for this quantity, the quantity mu. And in that particular case, because we have already, these are standardized quantities. They are now standardized quantities. So we can say that on the left-hand side, we can say that this is a standardized quantity Z1 less than or equal to x bar minus mu over sigma divided by root n. I'm conveniently leaving this that way so that we are able to get the interval we are looking for. Less than or equal to the upper interval, we can call it Z2. Now from here, at this point, in this case, now what we need to know is that because of how we have standardized, we have performed this operation of standardization, what we need to know is that Z1, which is equal to Q2 minus mu all over sigma over root n, this one has a standard normal distribution. Also, Z2, which is Q1 minus mu all over sigma divided by root n, this one also has a standard normal distribution. That is why now, instead of writing all this, we just reduce them to Z1 and Z2, where Z1 and Z2, they are real numbers. They are real numbers. They are real numbers that we are going to use in identifying our interval. So once we have that interval expressed as such, we now make mu the subject. We now make mu the subject. If we make mu the subject, then it means that we are going to try and rewrite all this. First, we must cross multiply the denominator of the middle term so that we have Z1 multiplied by sigma over root n less than or equal to x bar minus mu less than or equal to Z2 multiplied by sigma over root n. Now, that is the first step. Now, at this, once you make, to make mu the subject, because we are interested in the interval, the confidence interval for the population parameter mu, we just need to make mu the subject. One way is we subtract x from that lower interval and subtract x from the upper interval, so that we are going to have z multiplied by, we are going to have z multiplied by sigma over root n minus x bar less than or equal to minus mu less than or equal to minus x bar plus Z2 multiplied by sigma over root n. And then as an algebraic operation, now, because these are linear inequalities, these ones here are linear inequalities. We are interested in making mu the subject, but what we have is not mu. What we have is negative mu. So to make mu the subject here, we have to divide everything by -1. If we divide everything by -1, we will have made x bar the subject, or rather we'll have made mu the subject. So if we divide everything by -1 in this particular case, it will imply that x bar plus z sigma over root n, there's a multiplication sign there, is greater than or equal to mu, which is in turn greater than or equal to x bar. Sorry, because I am making mu the subject.
Why don't you equate them separately?
You can as well do so. You can as well do so. You can as well do so separately. There is no limitation on how you are going to do this. So in dividing everything by negative, the coefficient of the first quantity will be negative. So here is supposed to be negative. This one is supposed to be negative. The coefficient for x bar will be positive. That's why it's positive there. And then because we are dividing by -1 and they are inequalities, whatever was less than or equal to becomes greater than or equal to. That is how the operations for inequalities operate. So we have that the coefficient of x bar will be positive. The one for z will be minus. So minus z2 multiplied by sigma over root n. Now, in this particular case, now what we are going to have, because of this illustration, I think there's something I have to state before even coming down here. These Z2s are defined in that. Now, because Z1 and Z2, they are standard normal, it means that they are points on the curve. They are points on this curve. So there is one point on the lower limit, there's another point on the upper limit. So, and since this curve is symmetric about a point 0, it means that the point on the lower tail is negative. So in this particular case, Z1 is negative and then Z2 is positive. Because they are standard normal, they lie on this curve. And then the one on the lower tail is negative, the one on the upper tail is positive. So that brings me to this point here. This should be negative, sorry. Z1 will be a negative value. Z2 will also be a positive value. Z2 will be a positive value. So that's if this is negative, then the coefficient will be positive. For the Z2, the coefficient will be negative because we have divided through by -1. Now, in rewriting this quantity here, that expression up there is the same as, because mu is greater than x bar, or rather because x bar plus z sigma over root n is greater than mu, which is in turn greater than x bar minus z2 sigma over root n, then it means that this is the smaller quantity. This is the smaller quantity. And this is the larger quantity in that interval. In this interval, this is the smaller quantity, that is the larger quantity. So we can rewrite this whole expression so that now our confidence interval becomes x bar minus z2 sigma over root n less than or equal to mu less than or equal to x bar plus z1 sigma over root n. Now, in this case, this is a real value. The lower limit here is a real value, and the upper limit, the upper interval is also a real value. So that implies that now what we need to be able to get exact values are the quantity where x bar will be calculated from the sample quantity. This one is the sample mean, so it can be calculated once you have your sample. N is the sample size. Sigma is the population standard deviation. Sigma is the population standard deviation. But if you do not have the population standard deviation, you can use the sample standard deviation to calculate it. So for this expression here, you can use it when sigma is known. When you know the population variance, then you can use this particular approach of calculating the confidence interval. So this interval is used when the population variance is known. However, if you do not know the population variance, then you have to calculate or estimate it using the sample elements, the sample data that you got. So you can also calculate your confidence interval to be equal to x bar minus z multiplied by s over root n less than or equal to mu less than or equal to x bar plus
z when you get down. See the way you're wearing the mask.
N.
So you're not wearing it well. Get down. Watch it with the edge. Right.
So please know that if you know the population variance, you can use the first approach to calculate your confidence interval for a population parameter. And if it's not known, you can use this approach here to calculate the population parameter. Now, in this, it's important to note that because this curve is symmetric, these values, the z values are obtained from a standard normal table. These z values are obtained from a standard normal table.
Pour this. No. You go, I'm coming. I'm taking something. Semi. And sir, we don't know, I'm calculating it.
So it means that because remember, like I told you, this curve is symmetric. Therefore, whatever is on the upper side, whatever is above 0 is a complete replica of what is on the lower side or the left-hand side of 0. So this Z2 is always a negation of Z1. And Z1 is a negation of Z2 because the curve is perfectly symmetrical. The curve is perfectly symmetrical. So if you read your table and you get Z1 to be equal to, let's say, minus 1.34, then Z2 is just a negation of Z1, which will be 1.34 because of the nature of that particular curve. So the quantities Z1 and Z2 in this confidence interval will always be obtained from statistical tables. And for you to be able to obtain the values in the statistical tables, you must define your level of significance. The alpha level of significance has to be defined, and then you use that alpha level of significance to identify the values of Z1 and Z2. That is what we have. Now, in this particular case, whatever I have done here, this approach, you use it when this approach, you use it when n is greater than or equal to 30. If n is greater than or equal to 30, then use the above approach. We use the two approaches there, depending on what is known and what is not known. However, if n is less than 30, Then we use the student's distribution. We use the student statistic T. We use the student statistic T. So in place of Z, we are going to have T at n-1 degrees of freedom. That is, our confidence interval will be equal to X bar minus T at n-1 degrees of freedom multiplied by S over root n less than or equal to mu less than or equal to X bar plus T at n-1 degrees of freedom multiplied by S over root n. That is when your sample size is less than 30. This is the approach that you should use. Now, again, remember, like I told you, in deriving these intervals, you realize it's an interval. We have the upper limit, the upper interval, and we have the lower. So it means that you have to use the two-tailed test. You have to assume that your graph is of this form. You have to assume that your graph is of this form and therefore use it to identify the correct values of Z or T. Use it to identify the correct values of Z or T. And that is what we are having here. That is what we are having here. So if the population variance is known, you can use the first approach. But if sigma is not known, you can estimate it using the sample data. If n is less than 30, and you do the same for that. So it's an easy approach to apply when you are trying to calculate these quantities. Any questions? Okay, so we have this example here. This is an example on this particular section for estimating confidence intervals. And let us see how this can be calculated. Yes, Silas. Silas has a question. Please unmute yourself.
Yes, I mean, initially I was blocked. It's like the administrator has blocked us, but it's now okay. I wanted to find out, you keep on mentioning degree of freedom. I've done that, but if you can explain to me what is meant by degree of freedom briefly.
Usually, when we are, especially in the cases where we are trying to estimate population parameters using sample data, we tend to lose some information because not every element in the population is used in the estimation. So we lose some information. And this information that we lose is what in statistics we say that we are losing some degrees of freedom. So we expect that the results that we get will not be accurate up to a certain level. There's a level beyond which the accuracy is not 100%. The precision is not as maximum as expected. So in statistics, what usually happens, how you can determine the degrees of freedom that you lose is by identifying the number of parameters you are estimating. Identifying the number of parameters that you are estimating. Now, if you look at the student T distribution, it is very specific on scenarios in which it can be used. The student T distribution is very specific on scenarios where it can be used. And those particular scenarios are cases where N is strictly less than 30. So it means that the T distribution is more efficient when you have very small sample sizes. When you have very small sample sizes, then the T distribution is efficient. However, small sample sizes mean loss of information because of the size of the sample that has been used. There is loss of information. And therefore, statistically, we determine that we equate that loss of information to some degrees of freedom. And in this case, our degrees of freedom will be determined by the number of population parameters you are going to estimate. So for instance, if we look at this case, we are only estimating one population parameter mu, and that population parameter mu is estimated, we are saying that it can be estimated using X bar. So if you have a sample size of N, if you have a sample size of N, and you are estimating one parameter, then we say that you are losing 1 degree of freedom because of this parameter that you are estimating. So it is very specific. The issue of loss of degrees of freedom is very specific to the sample size. And that is why you can see that we are saying that if N is any value greater than or equal to 30, then in that particular case, we say that in that particular case, we say that we are having a scenario where there is a sufficiently large sample size, depending on your population and the ideal sample size. So we say that there is sufficient sample sizes that you can use to estimate, and we do not expect reduction in accuracy or efficiency of the estimator in that regard. Silas, have I tried to respond to your question?
Yes, please. Yes, I think it's okay.
Okay. So here there's an example. There's an example we have here, and we are told that a national magazine claims that the average college student watches less television than the general public. The average college student watches less television than the general public. The national average in terms of hours that people take to watch television, the national average is given as 29.4 hours per week, with a standard deviation of 2 hours, And then we are told that a sample of 30 college students is drawn. And from this sample of 30 college students, they found that the average time they spend on television is 27 hours. The question is there enough evidence to support the claim at alpha level 0.01? That is the question. So now in this particular case, first of all, I think this question is misplaced because we are asking if there is enough evidence. Okay, in this particular case, there are two things. you test the hypothesis if there is enough evidence at this level of significance. And also you can calculate the confidence interval. You can calculate the confidence interval. Now, let us first of all see how we can calculate the confidence interval using the information that we are given here. Now, in this case, we are told that the national average for what the national average in terms of hours that people take to watch television is 29.4 hours with a standard deviation of 2 hours. So what we can say is that according to this problem, the national mean in terms of the hours spent to watch television meal is 29.4 hours. And it has a standard deviation sigma of 2 hours. That is the standard deviation. Now we are told that a sample of 30 students is picked. So our sample size N is equal to 30 students. The sample size N is equal to 30 students. And from this sample size, they found that the average time they spend to watch television is 27 hours. So we can say that from this sample size, there is a sample mean of 27 hours. Now, I want us to try and calculate the confidence interval at alpha equal to 0.01 or 1%. So at alpha equal to 0.01, which is equivalent to 1%, we want to derive the confidence interval for this population mean. Now, in this particular case, because N is equal to 30 and the population standard deviation is known, this is the population standard deviation, then what we are going to use, this expression up here. This expression is what we are going to use. That expression is what we are going to, sorry, not that expression. This expression here is what we are going to use because sigma is known, and then we also know the corresponding standard deviation for the population. So we are going to express our confidence interval to be equal to X bar minus Z multiplied by sigma over root N less than or equal to mu, which is in turn less than or equal to X bar plus Z2 sigma over root N. We already know sigma. We know sigma. We know mu. Mu is given as 29.4. Sigma is given as 2 hours. And we also know X bar, which is 27 hours. So the task is to identify the values of Z1 and Z2. That is the task. Now, for us to, at this level of significance, we have to use this curve. So this is, it's not perfect because it's a sketch. It's not a perfect illustration, but It's symmetrical about this point. Now, alpha is the level of significance. So it means that in here, it's 99% of the probabilities. And then these regions here will share the spoils. The regions there will share the spoils. So we are going to have this region here to have a probability. This region here will be 0.01 over 2. And this region here will be 0.01 over 2 because they're sharing the spoils. Now we want to identify the value of Z1 and the value of Z2. Now, remember, like I've told you, the area under the curve represents probabilities for our possible values, of the population quantity probabilities. So as we proceed to the right, the probabilities keep on accumulating. And therefore, there are two ways in which you can do that. Because this curve is perfectly symmetrical. Once you know the value of Z1, you just need to negate it to get the value of Z2 because they are exactly, the accumulated probabilities will be equivalent. So from the lower tail, we are accumulating probabilities from 0. The least value of the probability will always be equal to 0. So we are accumulating the probabilities up to a point Z1. Now we are interested in this point Z1. We are interested in that point Z1 that has probabilities that have accumulated up to 0.01 divided by 2. I suppose that these accumulated probabilities are equivalent to 0.005. So this is how our standard normal tables look like. This is how our standard normal tables look like. And whatever we have in here, whatever we have inside these quantities that are 0 point something, all those are probabilities. All these are probabilities. And then Z1, or rather the Z values are listed over here on the left column. All those are possible values of Z values. Now, what you note is that from the least value of Z, as you progress, the values of the probabilities keep increasing. Those values of the probabilities keep increasing as you keep on increasing the value of Z. Now, these probabilities, you realize at the point 0, at this point is where the value of Z is equal to 0. At the point 0, the accumulated probabilities are exactly equal to 0.5, which is 50% of the probabilities in that curve. This is 50% of the probabilities in that curve. So at this point, at this point 0, at this particular point 0, the accumulated probabilities need to have accumulated to a point of 50%. And that is what this illustrates. So you have those, you can see the probabilities keep increasing. Now we have the positive values of Z, the ones that are above 0. The probabilities keep increasing up to a point where the last value of the probabilities is, you realize that at this point, the maximum value of the probability is given by this quantity here, the one as at the bottom right. This quantity gives the accumulated value. Now, what is happening is that these probabilities, you can see this one is very close to 1. It's very close to 1. because these tables are calculated, these values are tabulated at different values. Now, what will happen is that any value of greater than 3.9, a value like 4.0, we take the accumulated value of the probabilities to be equal to 1, anything that is up here. So now what we are going to do is that for this case of ours, the accumulated probabilities up to the point where Z1 is are 0.005. Those are the accumulated probabilities up to the point where Z1 is. So what we do, we come into this table and look for the probabilities, the probability 0.005. So we come in here and we look for the probability 0.005 inside the table. So because it's a very small probability, it's likely to be on the lower tail. That's why I'm scrolling up here. And at this point, we need to identify 0.005. Now, if we look at this table, 0.005 should be somewhere here. Okay. 0.005. Please note these two values. These two values. Between these two values, we have a probability 0.0025, or rather 0.005 between these two values here. Now, what happens is that it means, or rather the meaning of this is that our value of Z lies between these 2 points. Our value of Z lies between those 2 points. So I shall show you how we are going to obtain those values. Let me just reduce this. Okay. Now, the value of Z that is giving us the probability 0.00508, the value of Z that is giving us the probability 0.00508 is going to be equal to minus 2.57. Now, these quantities up here are decimal places, additional decimal places. So for instance, for this one, for this quantity here, the Z value is minus 2.57. So whatever is on the first row, whatever is on this first row is the second decimal for Z value. It is the second decimal value for Z value. So we can, from that particular table, minus 2.57 give us the probability 0.00508. And then this value, the probability that is here, the probability of 0.00494 is given by the Z value of minus 2.58. So minus 2.58 gives us the accumulated probability 0.00494, which means that our value of Z1 is between these 2 points. Our value of Z1 is between these 2 points. It's between 2.57 and 2.58. So because of this, what we usually do, because that value is between our value of interest Z1, it's between, our value of interest Z1 is between these 2 points. Just to note, our Z1 lies somewhere here. Now, what we are going to do, in such situations, what we do, we just take the average of these 2 values. The average of these 2 values. And whatever we get will be our approximate value of Z1. So in this case, we can say that Z1 is equal to the average of minus 2.57 and so we can say that Z1 we can say that Z1, Z1 is an average of these 2 points, minus 2.57 plus minus 2.58 divided by 2. And this average, if you find it, if we find this average, this is minus 2.575. So we take this value as an approximate value of Z1. We take this value because it's lying between these 2 points. And indeed, if you calculate the average of these 2 probabilities, you'll get that it's 0.005. It's very close to 0.005. If you find the average of these 2 values, you'll find 0.005. So we are not wrong to say that minus 2.575 is an approximate value for Z1. Now, once we have identified Z1, then Z2 is a negation of Z1 because the curve is symmetrical. So we can say that Z2 is 2.575, which is just a negation of Z1 because the curve is symmetrical. So we obtain those values of Z1 and Z2. And with this information that we have up here, we just substitute into that expression to get our confidence interval. So in this particular case, our confidence interval will be equal to X bar is 27 minus, in this particular case, we have, now remember that in our derivations, Z1 is already considered to be negative. So we are going to have minus 2.575 less than or equal to 2.75 multiplied by sigma, which is 2, divided by the root of the sample, less than or equal to mu, which is in turn less than or equal to 27, plus, this is the upper quantity, 2.575 times 2 over root n. So if you are able to calculate this quantity, you get the lower value of the interval. And if you are able to calculate this other quantity here also, you are able to get the upper value of the interval. You are able to calculate the upper value of the interval. So with this respect, please note that in this case, the Z values will be determined by where the accumulated probabilities are. Now, just to confirm the value of Z, what we can do is that, remember that the accumulated probabilities up to this point where Z2 is, the accumulated probabilities are 0.995. 0.995. That is 0.99 that is in here plus 0.005. So 0.995. And if we come to this table, for you to identify Z2, you look for the accumulated probability of 0.995. So yes, we come to this, and because 0.995 is on the upper tail, we'll just go to the positive values of Z. And in here, you look for the value 0.995. Now, if we look at this point, the value of 0.995 is between these 2 points. The accumulated probability of 0.995 is between these 2 points. And if you do the average like we did, you'll exactly get the value of 2.5. You'll get the exact value of 2.575. So yes, that is how you identify the Z values from the standard tables. Whatever you have in here are accumulated probabilities. So you need to find the Z value on this column. You have to find the Z value on this column that corresponds to that accumulated probabilities. Sometimes, depending on your alpha level, sometimes you may not get the exact value of probability and you have to do the approximation like we've done, but sometimes you do get exact values. Sometimes, most of the times actually, you do get exact values. So you may be lucky to get exact values for the Z values in the exact accumulated probabilities from this table. So you use your calculator and obtain these quantities. Once you are able to obtain those quantities, then you say that you have your confidence interval for that particular problem. Any clarification? Now, in this case here, now that is how you calculate the confidence interval. The confidence interval for a parameter like the population mean. Now, in the next case, we are having cases of inferences. Now, in this, you can see we are saying that we want to make inference about the difference between two means. What happens here is that you are having two populations, and in these two populations, you want to compare. Are the two populations the same? Of course, the comparison is made with respect to the parameter of interest. It's made with respect to the parameter of interest. And therefore, you are going to compare two populations using these parameters of interest. Now, in this particular case, we are assuming we have two populations. The assumption here is that we have two populations. Please, if you have a question, you can raise your hand or type a message on the chat. I have muted everyone there because I realize some people are having their mics on and they cause a lot of interference. So when we are talking about inference for two populations, what happens is we have population 1 and you have population 2. We have population 1 and we have population 2. And we are interested in trying to see if these two populations are similar with respect to a particular population parameter. Now, in this case, I'll be talking more about the simplest population parameter, which is the population mean. So we say, suppose that population 1 has a population mean mu1. Population 2 has a population mean mu2. For both populations, you draw a sample and estimate the sample mean. So X bar to be the sample mean of the first population and X bar 2 to be the sample mean of the second population. Now, assuming that I can see Silas requesting for a reference book. Yes, I can share a reference material that you can use to back up what we are doing here. So please, I remember to share it. If I forget to share it, alert me via your course rep. So the assumption here, the main assumption for comparison in statistics is that the two populations are independent. They don't share any common characteristics. So population 1 is very distinct from population 2. But we want to see if there is a difference in which a particular characteristic exhibits in either of the populations. Now, if X1, X bar 1 and X bar 2 are two sample means, if X bar 1 and X bar 2 are sample means from populations that are independent, then the expectation of X bar 1 plus the expectation of X bar 1 plus X bar 2, this is equal to the expectation of X bar 1 plus the expectation of X bar 2. Remember, X bar 1 and X bar 2 are sample estimators of the population means respectively. X bar 1 for population 1, X bar 2 for population 2. And because the two populations are independent, this rule of expectation is true for independent populations. This is true. And remember, we saw that X bar 1, the expectation of X bar 1, this is mu1, and the expectation of X bar 2 is mu2. So for independent populations, the expectation of X bar 1 plus X bar 2 is equal to mu1 plus mu2. And that is what we have there. In this particular case, it is an addition because we are trying to sum the two. However, if you are checking for difference of means, if we consider difference of means, in mean values, if we consider the difference in mean values, then it will imply that we are looking at the expectation of X bar 1 minus X bar 2. and this should be equal to mu1 minus mu2, using the same argument up there. Using the same argument up there, this is also true. So it means that if the difference between x bar 1 and x bar 2 is equal to 0, then the two populations are likely to exhibit the same characteristic. Otherwise, they are different. So this is for the case of the difference of means, and also for variance for independent populations. For independent populations, the variance of x bar 1, the variance of x bar 1 minus x bar 2, because they are independent populations, this is going to be equal to the variance of x bar 1 plus the variance of x bar 2. Now, at this point, I know you are going to be a bit lost because these are statistical results that can be proven. They are statistical results that can be proven. So do not worry about the equality of this. It can be proven that the two quantities are equal. So in this case, we know that the variance of x bar 1, because this population 1, it had a mean mu1 and variance sigma squared 1. Population 2 had mean mu2, variance sigma squared 2. Now, in this case, for a sample of size n1 from population 1 and a sample of size n2 from population 2, a sample of size n1 from population 1 and n2 from population 2, we can say that the variance of x bar 1 is equal to sigma 1 squared over n1, and the variance of x bar 2 is sigma 2 squared over n2. Remember, in general, for a random variable x bar, the variance of x bar can be proven to be equal to sigma over n, sigma squared over n. So if x bar 1, if these are the characteristics of population 1, if these are the characteristics of population 1, and this is for population 1, and the other one is for population 2, then we can say that our variances are expressed in this form respectively. This is how the variances are. And that is why here we are having it as this. Now, the reason as to why the variance is expressed this way is because of independence. Independence here means that the units in population 1 share no common characteristic with units in population 2. And therefore, there's not going to be any covariance. There's not going to be any interaction between population 1 and population 2. There is someone asking about a formula. Matilda, I do not understand the formula you're talking about. Maybe you can clarify. Matilda, you can clarify the...
Hello, doctor. Yes, the workboard, variance x1 minus x2.
x2.
It said it's equal to variance x1 plus variance x2. So that's why I said, can you please check the formula?
Yes, it's correct.
Okay. Why is it not minus, but it's positive?
It's because of the theoretical definition of variance from first principles. Now, if we derive this variance from first principles, this is what we will get. Irrespective,
Okay.
now, yes,
Okay.
just a moment, please, Matilda.
Okay.
It's important that I also clarify that if we were to find the variance of x bar 1 plus x bar 2, it will still be equal to the variance of x bar 1 plus the variance of x bar 2. Now, the reason this is happening is because there is zero interaction. There is zero interaction between the units in population 1 and the units in population 2. However, the effect of the difference would come in if there was interaction. If there is interaction between units in population 1 and units in population 2, then we will see the effect of the difference. We will see the effect of the difference, because now in that particular case, the variance of x bar 1 minus x bar 2 will be equal to the variance of x bar 1 plus the variance of x bar 2 minus twice the interaction between x bar 1 and x bar 2. That is where now the effect of the interaction comes in. It is at this point where it will be felt. But because we are having zero interaction between x bar 1 and x bar 2, the whole of this quantity is equal to 0, which implies that now that particular expression reduces to what we have up here. This expression, it reduces to what we are having up here. It's because of zero interaction between x1 and x2. Please note that this result, we can derive it. We can derive it and show you how it comes to this. But there are statistical methods that we apply to arrive at this point. And I do not want to go, not unless you people want us to do so. Unless you people want us to do so, I don't know. Maybe Matilda, I have to meet you on the side and explain this, but it's a statistical result that I can prove to you. I don't know if that has helped respond. You had another question too.
Hello, Prof. I'm okay.
Are you sure?
Yeah, yes, I'm okay. So my understanding is that if there's no interaction, although you have the minus sign in the formula on the left, in the formula on the right, you have to keep it as
it is positive, yes.
Positive
yes.
sign, so I'm fine. Yes, I'm okay.
Yes,
I'm okay.
If there is no interaction, it will be positive.
Okay, thank you.
Yes, yes. Any other question? Okay, so that is why we are having the variance of the difference of means expressed as that. The variance of difference of means expressed as that. And now, with this definition of the expected value of the difference of means and the variance of the difference of means for these two populations, then we can write down the corresponding statistic for the difference of means. And the corresponding statistic for the difference of means, in this particular case is going to be as it is here. The way Z is defined there, this is the statistic for the difference of means. That is the statistic for the difference of means. And we need to know how we can distinguish between the two. We need to know how we can distinguish between the two so that there is no confusion. Whatever we had at the beginning, now what we had up here, there is a point here, we had statistics. This statistic here is for a single population parameter. But what we are having down here is for two parameters because you have two populations. So you have the difference of means, less their expected value divided by their corresponding standard deviation. That is how we obtain the statistic for two population parameters, the difference between two population means. Now, once we have this now we can write it in this form, or again, we can write it in this other form. We can write it in this other form. So the T, you realize that now here we are having T. Now this T, the test statistic T, is used when N1 plus N2 are less than 30, or when we also do not know the corresponding standard deviation. Now, if we do not know the corresponding standard deviation, we have to estimate, we have to use the sample standard deviation or sample variance. So we have to calculate S squared so that we can use it in this form. So the methodology is the same as the case where we had one population parameter, but now here, because of we are interested in the difference between these two means. We are interested in the difference between these two means, x1, x bar 1 and x bar 2. These are the corresponding statistical distribution for that difference. These two give us the statistical distribution. These two give us the statistical distribution for this difference of means. And once we know the statistical distribution, you can come up with the necessary test statistic. So this is how we have our test statistic. Now, for T, unfortunately, you do, or rather not unfortunately, you note that for T in the denominator, we are not having S, we are not just having S squared. We are having S squared subscript P. We are having S squared subscript P. Now this S squared subscript P is a pooled variance for the two populations, a pooled sample variance. So if you have two distinct populations and we want to test for the, we want to make inference about the difference between means, we must calculate this pooled variance. And the pooled variance is calculated as such. It's important to note that S1 squared is the sample variance for population 1. S2 squared is the sample variance for population 2. N1 is the sample size for sample 1. N2 is the sample size for population 2. Now, with respect to the degrees of freedom, you realize here we are saying that we are having N1 plus N2 minus 2 degrees of freedom. Now, this minus 2 degrees of freedom is because of the two population parameters, mu1 and mu2. So you have to find the total sample size, which is N1 plus N2. N1 plus N2 gives you the total sample size. And then you subtract the two population parameters, the two degrees of freedom that we are using due to these two population parameters. That is why we are saying that for this difference of means, we are going to lose 2 degrees of freedom because of these two population parameters. Now, once we know our test statistics, we can also calculate the confidence interval for this difference of means. Now, in this particular case, for the case of one population, we can write this confidence interval as, to be equal to X bar plus or minus Z at alpha over 2, because the Z value is read at the tails, the 2 tails. Alpha over 2 is because of the 2 tails. And then we multiply this by sigma over root n. Now, if this is a generalization of that confidence interval. Now, if you take X bar minus Z sigma over root n, you have the lower value. If you take X bar plus or minus Z sigma over root n, you have the upper value. Just a moment, please. So in this case, in the case where we are now looking at a difference of means for 2 populations, now our confidence interval will be equal to, we are no longer looking at just X bar, but we are looking at X bar 1 minus X bar 2. And then plus or minus the Z value multiplied by sigma over root n. That is the confidence interval. That is the confidence interval. And that is what we are having in this case here. Now, of course, if n1 plus n2 exceeds 30, you use the normal distribution. You use Z values. But if n1 plus n2 is less than 30, then you use the student T distribution. You use the student T distribution. Now, that is the difference. And also, as long as that is happening, you have to calculate the pooled variance. We have to calculate this pooled variance. It's very important that it's calculated for you to be able to get that confidence interval. So that is all with respect to inference between the difference of 2 means. And you can see still that is what we are having here. We have it there. This is just another way of rewriting our test statistic T. And in this particular case, note that there is a condition for this particular test statistic. So in this particular case, if we have these two conditions, then your test statistic becomes that. The test statistic becomes that. And the corresponding confidence interval for that statistic is calculated in this manner. Note that in this particular case, for this case, you realize that we are not using a pooled variance. Remember that for this case up here, it is due to the equality of variances for the two populations. The equality of variances for the two populations, if that happens, then that is your test statistic. However, if the variances for the two populations are distinct, then this becomes your test statistic. This one here becomes your test statistic, and your confidence interval is calculated in that way. Now, the same thing can be done for paired samples, because you can have scenarios where you are pairing samples. You can have scenarios where you are pairing samples, and if you have samples that you are pairing, then the test statistic for the paired samples is equal to that. Now, in this particular case, note that we are having matched pairs of samples. So from an experiment, we can generate matched pairs of samples, and these samples are not necessarily independent, but are related. The samples are not necessarily independent, but they are related with respect to the parameter of interest. Now, if that is the scenario that is presented to you, then this is how you are going to calculate your T statistic, the statistic for that particular sample, for those paired samples. And in this particular case, X bar script D is the mean difference for the paired samples. X bar script D is the mean difference of the paired samples, and mu D is the mean difference for the population that you used. The corresponding standard deviation is also calculated, and the confidence intervals are given as such. The confidence intervals are given as such. So please note that this case is particular to paired samples. We know that in experimentation, you could be having a scenario where you are pairing your samples. And if that scenario arises, then this is how you are going to calculate your T statistic and corresponding confidence intervals. Now, with respect to the population proportion, remember for the population proportion, here we were considering a scenario where our population can be categorized into two, can be divided into two distinct subsets. One subset has the characteristics that you're interested in, while the other subset has units that do not involve the characteristic that you have. Now, what happens is that in this population of interest, you can draw a sample, and in the same manner, either a sample unit has the characteristic of interest or not. And we were able to see that in that particular case, if P hat is the population proportion of interest, if this is the population proportion of interest, the expected value of P hat is equal to the population proportion P. And this we found it to be equal to n over, we found this population proportion to be equal to n over A. Now, for this particular case, and we also found the variance, the corresponding variance for the population proportion. So the variance for the population proportion was equal to what is highlighted there. But like I said, for any, when we are talking about sample means, sample quantities, and especially some, in particular, we are trying to estimate population quantities with the aid of samples. We saw it is true to say that their asymptotic distribution, their sampling distribution is almost surely normal. So that is why we are saying that this proportion is, the statistic for the population proportion is given by that. The statistic for the population proportion is given by that. And once you know the expected value, once you know the expected value of p hat, this p is the expected value of p hat parameter, estimator rather, and this, the denominator here is the standard deviation. And remember, like I said, this process of subtracting the expected value of the parameter and dividing it by its corresponding standard deviation yields a standard normal random variable. So that is why you can see that we are saying this is a standard normal random variable. Now with those, you can calculate the confidence interval. Again, the method of calculating the confidence interval is the same to that of X bar, because we already know the expected value of p hat, and we already know the expected value of p hat, and we also know its corresponding standard deviation. So it becomes easy to calculate the confidence intervals. So in this case, please note that it's important to understand the distribution of the parameter, the sampling distribution of the parameter that we are talking about. And once you get the sampling distribution of the parameter that we are talking about, it's easier to derive the confidence intervals in these scenarios. Now, please know how to do, the method is the same. The methodology is the same. What differs is the parameter of interest. What we were looking at up here, we started by looking at the parameter for one population at this point. Here we are talking about the parameter for one population. That is why we are only having X bar, because we are assuming one population. And then from one population, we introduced two populations. We saw the sampling distribution. That is the sampling distribution for the difference of the two means. And then the corresponding confidence interval can be calculated in the same manner as you are doing for the others. We are moving from this difference of means, and then we come to the case of the population proportion. In the same way, the population proportion has its sampling distribution, and that sampling distribution is normal. The sampling distribution for the population proportion is normal. That is what we have here. Normal with mean P, where P is the population proportion and that corresponding standard deviation. That is the sampling distribution. Once you know the two, you have that confidence interval for one population of population proportion. One population of population proportion. Now, if you introduce two populations, then you are going to have two proportions, P1 and P2. And you also check for difference of means for these two, or rather the difference between the two proportions, P1 and P2. So what we are having here is the difference between two proportions. And again, here we are assuming that that form of independence is there. The form of independence is there. That means there are no interactions. There are no interactions. That is why you can see that in our variance, in our standard deviation here, the first quantity here in this root sign, this first quantity is the variance of proportion P1, and the second quantity is the variance of proportion P2. Again, because of independence, there are no interactions. That is why we are having these results. Now, if we standardize, we also have this value of Z. If we standardize, we also have this value of Z, the random variable Z. And this random variable is what is now going to be used in estimating the confidence intervals. It is what is going to be used in estimating the confidence intervals. Now, I know that this particular session has a lot, it has a lot of sampling statistics that, and the results that we are using here are results that have already been derived and proven to be true. That is why I did not go through the in-depth derivation of the results that we have here, but they can actually be proven to be true. Now, these end results are what you will need to estimate the confidence interval of the population parameter of interest. This is what you're going to use in estimating the confidence interval of the population parameter of interest. It's important to know what you're looking out for so that you can construct the correct confidence interval. Now, I think it's already 3:30. I think we'll go for a 10-minute break, and then we come back and finish. Hopefully we finish up on what is remaining on categorical data. I hope that is okay. So please take a 10-minute break, and then we'll be back for the remaining section on categorical data. I suppose we can now resume. Now, I know what I've spoken previously is a bit complicated for you people. We are talking about, we were looking at statistical tests, and these statistical tests were dependent on the quantitative data that was obtained from the sampling units. So in that case, everything that we've done was so quantitative, and it means that the same methods that we use in analyzing quantitative data are not the same methods that will be used to analyze categorical data. Now, in that particular case, for the case of quantitative data, you saw that once you are able to identify your sampling units, you can take actual measurements. Now, in categorical data here, we are having a scenario where your data is not in quantitative form. Your data is not in quantitative form. So it means that it takes different form, and this different form, we are referring it to categorical data. That is, it is the kind of data that is categorized depending on what you're looking at. For instance, if you are talking about the health status of an individual, you are either healthy or sick. That is purely categorical, because you cannot measure the level of well-being of an individual. So you are either healthy or sick. You are either male or female. There's nothing in between there. You are either male or female, healthy or sick, happy or sad, small, medium, or large, things like those. Those are the kind of categorical data we are talking about. And I'm sure for people in social sciences or even in arts, this is the kind of data they'll be coming across. This is the kind of data they'll be coming across. And we cannot use the methods that we've described previously to try and analyze such kind of data. So that is why different tools have to be formulated for analysis of this kind of data, So we are saying that in scenarios where you cannot quantify the observation, in scenarios where you cannot quantify the observation because of the nature of research that you're conducting, then you can apply this categorical data. And in this case, it means that you are going to have levels. You are going to have levels for your observations. So this case, in these levels, we are going to define a new variable that we refer to as ordinal variables. These ordinal variables are they are categorical variables that have been ordered. They are categorical variables that have been ordered. And even in your research, when you are constructing a questionnaire, when you are coming up with a questionnaire for use, then it means that sometimes you'll find that in your questionnaire, you'll be asking questions. And in these questions, they could be, the response could be open-ended or closed. In that particular case, then you have to look for ways in which your respondents can give you the information that you want. Now, for instance, if we are talking about a patient's health status, it can be excellent, good, fair, or bad. Now, what you can do here is you can assign 1 for the status bad, 2 for the status fair, 3 for the status good, and 4 for the status excellent. So in that particular case, you have a scenario where you assign your measurements values so that if someone ticks 1, you know it's bad. If someone ticks 4, you know it's excellent, and such things. That is the kind of categorical variable that we are talking about. Another one is the case of gender, like I said, male or female. You can have, if you are interested, if your research requires you to talk about the race of individuals, then again, in that particular case, you can have the categorical, you can assign the values, the scales accordingly. You can assign the scales accordingly. Now, this type of observations cannot be analyzed. We cannot assume that they have normal distributions, no. Now, they can take different forms of distributions. And in that particular case, most of the time, if, for example, if we look at the case of, if maybe your variable is gender, you are either male or female. Now these types of nominal variables, they exhibit binomial and multinomial distributions. Remember, for binomial distributions, this is a scenario where the outcome is either a success or a fail, depending on what you're looking at. So if you pick a unit, it's either it was a successful pick or a fail. Even in manufacturing, either an item is good or defective. So if there is that scenario playing in your study, then you can say that your variable of interest is having the kind of binomial or multinomial distributions. Now, for us to be able to analyze that kind of data for a particular nominal variable, we will have to construct things we call contingency tables. Now, it's easier if, for example, once you ask questions, for example, you have a group of people in a room and you ask them, you give them a question. What about their gender? Someone will tick either male or female. Now, if we only have one variable of interest, then it will be easy to analyze that data, because all we need to do is count the number of males and count the number of females. From there, you know the categories that individuals lie. However, there are situations where we can have more than one categorical variables. Now, in that case, we have to use contingency tables. And in these contingency tables, the contingency tables is a tool that we use to easily analyze two categorical variables. It is a tool that we use to analyze two categorical variables. Now, for example, maybe you are in that room that has maybe 20 people. You can have two variables of interest: gender, male or female, and their health status, healthy or sick. Those are two variables. So you'll find that a male can be healthy or sick. A female can be healthy or sick. The only way you can analyze this data is you have to create a table. And in that table, you have a number of rows for one category and a number of columns for the other category. So for instance, in this particular case, if you have two categorical variables, X and Y, your contingency table will have I rows for the X variable, and it will have J columns for the Y variable. And then for each cell, in each cell of that table, you'll be able to now have the correct data. And it means that in that case, the cells are going to display all the possible combinations. For example, we can have, let's say this is the table, and we are saying that you can have I rows for the X variable, and then you can have J columns for the J variable. And then all the cells in this table, cell 1, cell 2, cell 3, cell 4, all the way up to cell 12, they'll have the possible combinations. They'll have the possible combinations. Now, let's suppose that in our table, we have a variable gender. Let's denote it by G. And you also have another variable on the healthy status. So maybe that is a variable on health status. And gender. So in the gender, you can either be male or female. You can be male or female. In the health status, you can be healthy, H, or sick. You can be male or female, and then in the health status, you can be healthy or sick. So the cells in here are possible combinations of the possible outcome. You can be male and healthy, or male and sick, or male and sick. You can be female and healthy, or female and sick. Now, this is a simple illustration of a contingency table for two categorical variables. And we are saying that one variable will have J rows, and variable X will have I rows, and variable J will have, variable Y will have J columns. Variable Y will have J columns. And the cells will consist of all possible combinations that can be as a result of what you observe. Now, that means that in that population, once you are able to collect all the information from these units from the units in your sample, this is the possibility. This is the possibility. So you'll know the specific number of males who are healthy. You'll know the specific number of males who are sick, specific number of females who are healthy, and specific number of females who are sick. However, if we sum the first column, you'll get the total number of individuals who are healthy. The first column gives you the total number of individuals who are healthy. The sum of the second column will give you the total number of individuals who are sick. Likewise, if you sum this row, you'll get the number of individuals who are males. And for the second one, if you sum the rows, you'll get the number of individuals who are females. So that is a contingency table. And it is easy. It is very easy to implement when you are having two categorical variables. And even in the data analysis, it's very easy to analyze. So here is another example of a contingency table for two categorical variables. In this case, we are assuming that you are trying to investigate individual belief on whether people believe on afterlife or not. There are those people who believe that there's an afterlife. There are those people who don't believe that there is an afterlife. So we take a group of people. In that group, we have males and females. And then we ask them of whether they believe in the afterlife or not believing in the afterlife. So in this case, you can see this first cell here is the number of males who believe in afterlife. The second one is the number of males who do not believe. The second row, in this case, we have the number of females who believe in afterlife. And here we have the number of females who do not believe in afterlife. But if you sum the values in this column, if you sum the values in this second column, you'll get the number of people the total number of people who believe in afterlife, and also the total number of people who do not believe in afterlife. Likewise for the rows. So in this case, we can say there were a total of 502 males and 625 females. Out of these 502 males, 398 believed in afterlife. The remaining 104 did not believe in afterlife. Now the question becomes, now that once you have this contingency table, the question is now on the association between gender and belief. Why is it that many females believe in afterlife compared to the number of males? Why is it that this number of people do not believe in the afterlife compared to this other number of people who believe in the afterlife? That is the kind of understanding that you'll be seeking to arrive at when you are talking about this kind of information. And I believe for most people in social sciences, this is the kind of information that they get. So in trying to understand the association between variables, we now employ non-parametric tests. Remember, because of the nature of our data is purely categorical. Because of the nature of our data, we cannot use the quantitative methods to estimate, to try and analyze the association between variables. But we have non-parametric tests. By non-parametric tests, we mean that you don't have to estimate a population parameter for you to be able to analyze your data. Remember, for the preceding quantitative approaches, you could see that we are estimating a population mean, we are estimating population variance, and so on. So that makes those approaches parametric, because you need a parameter for you to be able to estimate the confidence interval, for you to be able to check for the test of hypothesis and things like those. But in this case, for categorical data, you do not need to estimate population parameters. So we have other non-parametric methods that we use in this kind of data analysis. So in this case, we have reasons as to why parametric tests, non-parametric tests are favored in the analysis of categorical data compared to the other parametric tests. One, the circumstance under which we can use non-parametric tests is if the data does not support assumptions of normality or parametric assumptions. Remember, in the preceding section, it can be confirmed that any population statistic has an asymptotic distribution with its parameters. In this case, if your data does not meet those, you can use non-parametric tests. Now, another advantage here is that because we do not need to check for normality or even parametric, we don't need calculation of parameters, then it implies that we make fewer assumptions. So for non-parametric methods, we have very few assumptions that have to be made with respect to your data analysis. Now, another reason is that in this case, for categorical data, parametric tests would be difficult to apply if your data is not transformed into a suitable form. There are ways in which we can transform categorical data into quantitative data, but if we are not able to do so, then it means that you only have the option of using non-parametric tests in your estimation. So, and also remember, one, if your data is of nominal form or ordinal form, then you write off parametric tests. You write off parametric tests and go for non-parametric tests. So those are the main reasons or circumstances under which you can start They are the main reasons under which you can use non-parametric tests in your data analysis. So we have a number of non-parametric tests. The first one is the chi-square test for independence or association. Now, I'd like to clarify that we have a chi-square test for parametric tests, and we also have a chi-square test for non-parametric tests. This chi-square test is specific to non-parametric tests, and we use it to test for the degree of association between variables. For instance, in the preceding example, we can use it to test for the degree of association between an individual's gender and their belief towards that concept of afterlife. So in that particular case, the non-parametric chi-square test of independence comes in very handy in trying to analyze the association between the two categorical variables. And also, it's important to note that for these non-parametric tests, we have data analysis software such as Tata. These ones are inbuilt. They are inbuilt. As long as you are able to provide the necessary information, you can request for a chi-square test and it will be done. Depending on the outcome, you should be able to tell whether there is a degree of association or not between the two categorical variables. So that is the first non-parametric test, the chi-square test for independence. So please, if you have this kind of contingency table, let's suppose you have two categorical variables and you come up with this form of contingency table. The first thing you may want to look at is the level of association, because once you are able to determine the level of association or interaction between the two variables, then you will know the other step you need to take so that you can analyze your data further. So you use the chi-square test to check for independence. Another test that we have is the sign test. Another non-parametric test is the sign test. Now, this sign test is a non-parametric counterpart of the T statistic, the T test. This one is the non-parametric counterpart. You saw that for the parametric T test, we needed the mean, we needed the standard deviation, and we needed the degrees of freedom. Now, the non-parametric counterpart of it is the sign test, and it does not require you to get the mean or standard deviation, but you can use it to compare the middle points. You can use it to compare the middle points for the sample and population. So sample median and population median. Remember, for you to be able to use this sign test, you'll be required to arrange your data in ascending order. That is the only way you can be able to identify the median. The median of a population is that quantity that divides the population into two distinct sets. So if you consider a population, if for example, we consider a population of, let's say you have a population of 1, 2, 3, 4, 5. Now, at this point, you realize that the number 3 divides this population into two distinct sets. You have those that are greater than 3 and those that are less than 3. Now, in the sign test, what happens is that it will assign negative values. It will assign a negative sign for numbers that are less than the median value. It will assign a negative value for numbers that are less than a median value, and it will assign positive values for numbers greater than the median value. So in general, let's suppose that in your population, we have x1, x2, and then you have the median m, and then from there you have, or rather, instead of writing the median m, let me write xm to denote the median. Xm to denote the median. And then you continue with xm plus 1, that is the value after, and you continue so for each and every. Now, this xm is the median. The sign test, what it does is that for each value that is less than xm, it will assign a negative value. So for x1, it will assign negative. For x1, it will assign negative. For x2, it will assign negative. x3, it will assign negative for each and every value less than xm. For values greater than xm, it will assign positive values. For xm plus 1, it will assign positive value. For xm plus 2, it will assign positive value for xm plus 3, and so forth. That is how you use the sign tests to compare population medians and sample medians. Remember, for each category, you can arrange your data in ascending order. That is the first thing. If you want to use these tests, the first thing you have to do is arrange your data in ascending order. Once you arrange your data in ascending order, then you can identify the midpoint, that value that divides that set of values into two distinct sets. Once you identify the midpoint, every value less than the midpoint takes a negative value. Every value greater than the midpoint takes a positive value. So that is how you use that. And in terms of course, now, once you have used the sign test to identify values that lie below and up and above the median point, you proceed to do a rank sum test, which we call the Wilcoxon rank sum test. Now, this test here will be used for independent samples. Now, in this case, at this point where you have assigned negative and positive values, you'll find the sum. If these negative values are more than positive values, then you make the necessary conclusion. You will make your conclusions based on the findings on the number of negative values and the number of positive values. Now, this is the case where you only have one population or one ordinal variable, one categorical variable. But if you have more than one categorical variable, then we now have the Wilcoxon rank sum test. Now, in this case, the Wilcoxon rank sum test is similar to the student t-test for two populations. The Wilcoxon rank sum test is similar to this one up here. It is a counterpart. Let me find it. The Wilcoxon rank sum test is a counterpart of these parametric tests. It is a counterpart of this parametric test. So you have two populations that have their own features. And now for you to be able to analyze that particular set of data, then it's important that you use the Wilcoxon rank sum test. If you have two categorical variables that are independent of each other, then you proceed to this. Remember the chi-square tests. The non-parametric chi-square test is used to test for independence or the degree of association. Now, once you are able to confirm that the variables are not independent, then you can use the Wilcoxon rank sum test. Please note, independence here is very important because any form of association, of association of relation between two variables is bound to affect the results. So it means that if there's a degree of association, you have to look for an alternative way in which you can analyze your data. You have to find an alternative way in which you can analyze your data. And this alternative way will all be dependent on the results of the chi-square test for independence. So this the Wilcoxon rank sum test is mostly used when you want to compare two populations. And these two populations, they can be ranked or non-normal. By ranked here means that you do this kind of ranking. You can do this kind of ranking so that you are able to compare these particular variables. Now, note that it's very important in scenarios where you have independent, that is the condition. You must have independent samples for you to use the Wilcoxon rank sum test. Now, please, I have to reiterate that these non-parametric tests are inbuilt in data analysis softwares like Stata. They are inbuilt. All you need to do is call the command, and then for each variable that has been selected, you get a value. And once you get the value, you can do the interpretation before you can proceed to do other tests. So this is the condition. It can only be used in independent samples, the Wilcoxon rank sum test. And you need to have you need to have two populations, because the two populations is what qualifies for this Wilcoxon rank sum. Now, still, this is just an elaboration for the Wilcoxon rank sum test. Now, please, it's easy to implement these tests. It's easy to implement these tests and apply them compared to the quantitative or parametric tests. These ones are easier, but I think it's evident that each method of data analysis has its appropriate area of application. Now, for these ones, is the case where you have categorical data or data that cannot be analyzed using quantitative approaches. In that case, you use this method. These are the possible methods you can use to analyze the data. However, if your data, you make assumptions with respect to parameter estimation, you make assumptions with respect to the distribution of the parameter and so forth, then you just have to use the parametric tests for data analysis. You have to use the parametric tests for data analysis. So it's all dependent. Now, all these will be defined based on your objectives. And that is why I'll go back and say that how you define your objectives is very important. How you define your objectives is very important, because from your objective, you can tell whether you are going to use parametric tests or non-parametric tests. From your objectives, you can tell how you are going to identify your sample. Are you going to use probability sampling techniques, or are you going to use non-probability sampling techniques? So definition of objectives is very, very important in any form of data analysis, because that is the blueprint of the whole thing. And if your blueprint is not correct, everything will come crumbling down and you have to start all over again. And it's not advisable for us PhD students to experience that kind of turmoil. Already being a PhD student is psychological torture on its own. There are psychological problems that PhD students endure. You have to think of school, you have to think of family, you have to think of work, you have a lot of things that interfere with the psychological state of PhD students. But if you are not able to define your objectives correctly, your problems are bound to be compounded. And problems relating to your research are the most annoying, they are the most time-wasting things that you'll ever experience. So I advise correct definition of your objectives. Another thing that you also need to be careful about is when you want to go and collect your data. When you want to go and collect your data, please make sure that you identify the correct population. Identify the correct target population from which you can get your sample units. Now, again, if your population is not correctly, if you are not able to correctly identify your population, whatever results you are going to get from the sample are not going to be reliable. They are not going to be reliable. That is why you can conduct your research, you get to a point, maybe you get to a point where after 2 years, you realize that you are not getting what you're doing. And it happens it does happen, unfortunately, it does happen to people where you get to the advanced stages and then the people in the examination panel, they tell you that, no, this should not have been done this way. You have to go back and relook at how you did your thing so that you can get the results that you desired. And it is a roller coaster of emotions. It's a roller coaster of a lot of things that please, I would advise you try to minimize on. But all this is dependent on how you define your, objectives. Very important. If you are going to do experiments in the laboratory or in the field, it's important to do a pilot study. A pilot study is very important because it helps you rectify on areas that could have brought issues in the actual survey. Now, from the pilot study, you will be able to know what to add, what to subtract, what to modify, what you need to improve upon before you can go into the real study. And all those things help you in trying to save time. They help you in trying to save time and resources, which are all limited, as we know. So I think this marks the end of this session. This marks the end of this session on data analysis for quantitative analysis. Yeah. Quantitative research methods on the case of sampling distributions, hypothesis testing, and also inference. Now remember, from the samples that you have, you need to make inference on the entire population. That means that your sampling units, they need to be a good representation. They have to be representative of the population of interest. If your sample units are not representative of the population of interest, you'll get wrong results and you'll be forced to go back to the drawing board. If you allow your emotions to cloud your judgments, with respect to data collection, again, your results are going to be flawed and you may be forced to go back into the drawing board. So please be very careful when you are conducting your survey with respect, be very careful on those areas when you are conducting your survey. And once you are able to get all these things correctly, you'll spend less time trying to make corrections to things that could have been avoided in the first place. So this brings us to the end of this session, and I'll stop. Yes, there's a hand that has been raised up. Yes, Silas. Yes, Silas.
Okay, no, it took some time to unmute because, yes, Doc, thank you so much for the impact and the knowledge. My only maybe is lack of understanding, not of what you are doing, but I'm from the computer science department, and the way we run our experiment, I see most of the time, the earlier lecture by Dr. Anku and yourself, yes, it's more statistics and it's geared towards the chemistry and the biology. I mean, for the computer science, we don't actually, hardly do we collect data, but we run experiment. There are normally publicly available data sets that you run your models and your training against to show how high accuracy your model is, and that is the trend in our environment. But so I sort of find it hard to is it associate or have an influence on all that we are doing in relation to my field. I presume my other colleagues from the other department, let's say chemistry and things, but they associate more or more comfortable with what we are doing. But per my area, I don't know whether the next lecture will dive into areas of computer science and computing, but it has been a trend that almost all the lecturers are from the chemist and the statistics background, so it's geared towards that side. So I appreciate the lecture and all that, but how to bring that into my area to help my work. As I said, we hardly collect data. There are publicly available data set that you have to train your algorithm against, and if your algorithm prove to give better accuracy, is where we acknowledge you contributing something to knowledge. So yes, that is, I don't know if you can have anything to say about this, but that is just for me. And also last but one, just the reference material, please. I know you might forget. I'll try and remember our rep to remind you, but in case you don't, just try and share so that one could do a reading as well. Thank you very much.
Okay, thank you, Silas. I agree with you that not everything that we have gone through will be applied in your area. Depending on your area of interest, you may use some of the information from here, or you may not use the information. For example, if it's the case, it's in the case of, if you are trying to use that case of supervised research. Now, in that case, I agree there are inbuilt, you already have data that has been collected, and it is that data that you'll use to train your models and everything. But in the course of training your models, the analysis that is done is similar to what is done here. Now, in this particular case, for example, you can have an inbuilt set of data. You can have an inbuilt set of data on maybe people who are suffering from diabetes. And you would want to understand something with respect to that problem. So yes, you can take this data and use it. Remember, from this data, you can draw samples. Several samples can be drawn from that single set of data. And these samples can be used they can be used to train. If you are having a particular quantity in mind, you can use these samples to try and train and analyze data with respect to that area. I agree with you. So all the form of statistical simulations and even computational simulations and analysis that will be done, they'll borrow knowledge from here. That one, I do agree that maybe for you, you may not use this particular, you may not go to the field and use these particular methods, but even when you are using data that is readily available to you, you can still use these methods for your data analysis. And there is nothing wrong with that. There are two forms of data you can get. You can choose to go to the field and collect fresh data or raw data, or you can go to the available depositories and get data that has already been obtained from the field and stored there for future use by different people. So it is not mandatory that you have to go to the field. You can only go to the field if you are compelled. And maybe the reason as to why you are compelled is because maybe there is no prior data that has been obtained with respect to what you are doing. And in that case, you have no option but to go to the field. But still, as long as you have your data, whether it is primary data or secondary data, these forms of data analysis will come up and they can be used to analyze your data in the sense of trying to make your model as robust as possible. As for the reference material, yes, I agree that I will share material. I will share a simple book that you can use. I'll share a simple book that you can use to try and understand this. And yes, I am, with respect to what you are talking about, you realize that each of us is into a specific area of statistical data analysis. Dr. Aku took you through experimentation and the statistical tools you need to analyze your data for that case. I have looked at cases of sample survey and data analysis. The next one will also take you through another area of statistics, especially regression. And I think maybe because you're talking about training data and everything, you'll find the next session is likely to be more interesting to you because you relate to it more. It's more of developing robust models for your research. And irrespective of the area of statistics you find yourself, even people in computer science, they apply a lot of these things in their course of work. So irrespective of where you are, you find yourself borrowing knowledge from one area. Of course, we use computer programs. I use computer programs in sample surveys. In sample surveys, I can choose to use primary data or secondary data, depending on the parameter of the population I want to estimate. I can improve on the efficiency and accuracy of my estimator based on the methods of data analysis that I'll be having. So yes, I can even go borrow knowledge from people in health sciences. I can borrow knowledge from people in chemistry, because research does not necessarily have to narrow. Once you are done with being a student, other forms of research that you'll be doing, they don't necessarily have to be in your area of interest, but you seek to borrow knowledge from other areas and incorporate it into what you are doing so that you can come up with better tools that can be used in decision making, things like those. So as a computer scientist, you may end up finding yourself in the in the field of medicine, you can find yourself in many other areas. It's all about how you are able to incorporate all these methods into your problem to try and solve a problem that whose results can be relied upon for future references. So that is what it entails. You may not use it now because you are PhD students. Of course, you have to be specific to what you're doing. That one I understand. You have to be specific. But after PhD, you'll find yourself trying to borrow knowledge from a lot of areas and incorporating them into your problem. And that is where the difference comes in. That is where the networking comes in. So you'll find yourself networking with people from chemistry, you'll network with people from physics, people from mathematics, people from statistics, just to try and solve a problem that can alleviate suffering or can make things easier for people. That is what all this is all about. It is not a must that you apply this in your research, but there may be a point in time you'll need it, and that is why we are doing it. Any question? Any other question? So I'll stop at this point. Yes, Eric.
Oh, good evening, madam. Yeah, I just want to say thank you very much for the kind of words and encouragements. If I look at the way you've taught us, I believe it will go a long way to help all of us. We are in the physics department, and I believe you use most of the things that you have taught us. So I just want to say thank you very much.
Welcome, Eric, and thank you. So if there is no other question or comment, I'll want to say thank you to all of you for religiously turning up for these sessions. And I really hope that as you progress into your research, you find these tools to be useful in your research. I hope and pray that your period of study is smooth. I hope and pray that you do not come across obstacles that are going to, I hope and pray that you're not going to come across obstacles that are going to derail you. By obstacles, I mean psychological status. Like I said, I know that as PhD students, you are subjected to a lot of psychological torture. And that psychological torture can make you spend the longest time in your course of pursuit. So I really hope that all that you do, God is with you and He helps clear the path for you as you do what you intend to do. And I pray that you succeed in it. So I'll stop here. I see messages here. There is Vice President Hopeful, Peter Mensah, who wants to ask for your votes. Oh, sorry, it's Samuel. Okay, Samuel, you have time to speak to your potential constituents.
Okay. Good evening, colleagues. My name is Samuel Miden Combat. Please, can you hear me? Please, can I be heard?